we're talking about the constant modulus algorithm, CMA, and we're to discuss now how it is that the CMA can help us recover timing in the laboratory scenario, setting. So suppose that I have a continuous time signal. So here is my example, my raised cosine 25% pulse that I am sampling here, way over sampling, so it looks like continuous time. And suppose I want to sample this at 1 sample per symbol. Well, the logical thing to do is that you look at where in this time scale I have the largest eye opening in any given symbol time. I'm not going to sample here because it's not very open. This is the optimal sampling time when the eye is the most open. And as I mentioned earlier, commercial receivers have a dedicated clock recovery circuit that is finding exactly when this is and maintaining it at the correct location and time. However, in the laboratory, we don't have this available to us. So we cannot sample simply at 1 sample per symbol because we just don't know when that sample should be taken. So we are going to deal in the laboratory scenario when we're doing experiments with coherent detection. We're going to have to use a real-time oscilloscope. The real-time oscilloscope allows us to capture the signal and do offline processing. But of course, the real-time oscilloscope has its own limitations. It has a certain sampling rate, and of course becomes very expensive if we sample very, very fast. And so typically we're going to have a few samples per symbol at best for processing our signal. If we've got a really fast RTO, then what we're going to do, we're going to send our data really fast. And so in the end, we're dealing with a few samples per symbol is what's available. So if I only took one of those samples per symbol, I don't really know where it's falling, right? I haven't done any synchronization, and if I had a bunch of samples per symbol and then I just blindly picked one of them, I may fall at a very, very bad time when the eye is not open. And so this is not really an option in the test laboratory. So what I'm going to do is I'm going to use the CMA algorithm to help me deal with this situation, and I really require realistically a minimum of 2 samples per symbol in order to have really good timing recovery. You could get lucky with less, but to be robust, to be sure that you'll have good sampling time, you need 2 samples per symbol. More samples per symbol could give you higher performance, but generally it also gives you higher complexity. So 2 samples per symbol is a very common compromise in the laboratory. So suppose we're doing 2 samples per symbol, and I have plotted here, instead of the continuous time eye diagram that you're seeing here, I've gone and I've sampled that continuous time diagram at 2 points. And so now, of course, this is what I like to refer to as a fake eye diagram. I've actually got points at this time sample and points at this time sample, and then these yellow lines are just connecting those consecutive samples. So what's nice about 2 samples per symbol is I am assured to get, if it's really a 1, I'm assured to get some power in 1. I'm not going to be transiting in between the +1 and -1 and hovering at the 0 power, which I could get unlucky and be exactly at the transition point instead of being at the maximal eye opening. But if I have 2 samples per symbol, that's not going to happen. At least one of these is going to have power on it. I'm not going to be stuck at the transition. Now, it could be that at these 2, I happen to put it at either symmetric side of the ideal sampling time, in which case they'll both have some power in it. Or, it could be slid to one side, so I really don't know. But at 2 samples per symbol, I know I'm going to have enough to recover the data. So now suppose that I take these 2 samples per symbol, and I instead assume that I'd only had 1 sample per symbol. Well, I could have gotten lucky and had the pink one, in which case it's not at the maximum eye opening, but the eye is pretty open there. But I could have been unlucky and chosen the green one. And the green one, it's happening at the transition time. It has a closed eye. And so this is why it's important to do sampling at 2 samples per symbol. So we're going to go on and see what CMA does with these 2 samples per symbol. So it takes in the data that you process from the RTO, this continuous time samples that were saved, and it takes in the 2 samples per symbol, and it returns to you a signal at 1 sample per symbol. So it if I run the CMA algorithm exactly on this signal, it will deliver a very clean one at 1 sample per symbol. So this will be the 1 sample per symbol. It's not as clean as that ideal one that I showed you earlier. There is some thickness here to the rail up here and below, but of course it's much, much better than what we had before the CMA processing. So if we looked at the eye opening for the analog eye and what's coming out of the CMA at 1 sample per symbol, we've maintained the eye opening. But now we've just got our eye opening at the correct time. We have the correct time for our sample. Now, the CMA, when you initialize it, it could either try and improve things on the pink one, or it could try and improve things on the green one. It's got to be initialized at one of these two possibilities for 2 samples per symbol. And both of them will give you decent results. Here, I happen to make the right choice when running my CMA algorithm, or it just happened to come out of the RTO the right way. The one that I sync on in the CMA happened to be the good one from the RTO. And this is a convergence plot. So when CMA is a linear filter, and I'm adapting the taps in order to do the best kind of convergence I can. And this is super fast, so you don't see it, but boom, it goes down, and then it stays down. And that's because I'd chosen one of the samples that was already pretty close to the maximum eye opening. If I chose the other one, or it happened that I was using the other sample, it would take me longer to converge, but it would also work to recover. So even if I get unlucky, it's split between the two. I happen to be falling on the one, trying to increase the weaker one. The CMA algorithm takes all that into account and does well. It has slower convergence, maybe, at that point, because I got unlucky. Maybe there's a little bit more noise. You can see it because these rails are maybe a little thicker, but not much.